Welcome to part 4 of week 2. Today we will talk about quadratic functions, parabolas. So you know, of course, that the graph of the standard quadratic function y equals x squared is the parabola. But we will talk today about a more generic form of quadratic equations or quadratic functions written in the form a times x squared plus bx plus c. We will here assume that a is non-zero. For otherwise, if a is 0, we get a linear function. So to get a nonlinear function, we really need the assumption that a is non-zero. When talking about quadratic functions, a very simple procedure will be useful. I'm sure you saw it before. This procedure is called completion of the square. And it's done in generic form here. I think it'll be useful if we re-implement this procedure in a particular example. Let's say we want to complete the square in the function two x squared plus 5x minus 7. In general, ax squared plus bx plus c. The first step is always to factor out the coefficient in front of x squared, which is a. In my case, I factor out 2 to get x squared plus 5 halves x minus 7 halves. The next step is to view the first two terms as if they were the first two terms in the formula for square of a sum, right? When you square the sum alpha plus beta, the result is alpha squared plus 2 alpha beta plus beta squared. So we concentrate for now on the first two terms, right? Well, first of all, I want to create a 2 in front of b over a, so I multiply and divide by 2. If I do this here, I will get x squared plus twice times 5 over 4 instead of 2, x minus 7 halves. Now, we view x as our first number and 5 quarters as our second number, and pretend we are squaring the sum x plus 5 quarters. Right? If we were to square x plus 5 quarters, the result would be x squared plus twice the product, x times 5 quarters, plus the square of 5 quarters. Note that the first two terms we already have. The only part that we are missing is the last term. Well, to compensate for the last term, we will subtract it. So I will get x plus 5 quarters squared, and that again is x squared plus twice 5 over 4 times x plus 5 over 4 squared. And to compensate for this extra 5 over 4 squared, I simply subtract it. In general, we have x and we have b over 2a, and so we write this as square of x plus b over 2a. That will result in the extra term b over 2a squared, but to compensate for that, we subtract that term. See how these two terms cancel out. The rest is simply combining the like terms. We have x plus 5 over 4 squared. And when you combine the terms here, it'll be 25 over 16 minus 7 over 2. And when you do the algebra, that's 25 plus whatever you get when you add 25 over 16 and 7 over 2. The common denominator is, of course, 16. 16 divided by 2 is 8. 8 times 7 is 56. So when you add them, it'll be 83 over 16. All right. In general, when you combine negative square of b over 2a and c over a, you get 4ac minus b squared over 4a squared. Lots of different things could be noted here from this form of writing the quadratic function. It's much more informative than the original form ax squared plus bx plus c. For instance, we can immediately see that the expression in the brackets is at least 4ac minus b squared over 4a squared, simply because this is square and square is always non-negative. Right, the same here, this is always non-negative. So that gives us, in our example, an estimate of the lower bound of this function. This expression is at least twice negative 83 over 6 plus 0. In fact, as we will see later, this is the minimal value of that function. So it's a valuable piece of information. When we complete the square, we immediately find the smallest value our function can take. That is, of course, if a is positive. And if a is negative, we get the largest value that our function can take, because, again, the expression here in the brackets is at least 4ac minus b squared over 4a squared, attained when ax equals negative b over 2a. It's either greater or equal, if a is positive, than 4ac minus b squared over 4a squared times a, or less or equal than a times 4ac minus b squared over 4a squared when a is less than 0. Either way, so what we have just obtained is this. If a is positive, our function f takes its smallest value and the smallest value is a times 4ac minus b squared over 4a squared, which is of course 4ac minus b squared over 4a, and this value is taken at the value x negative b over 2a. And likewise, if a is negative, our quadratic function f takes its largest value, which is also 4ac minus b squared divided by 4a, again at x equals negative b over 2a. Either way, this point is very special, the point where x is negative b over 2a. It's called the vertex of the parabola. Negative b over 2a is the equation of this vertical line, x equals negative b over 2a. And this point is also special in a different way. The vertical line passing through that point, the vertex of the parabola, is also the axis of symmetry. What does that mean? It means that if you step away from that vertical line by some t in either direction, to the right or to the left, the value on the parabola will be the same. And that's easy to see why. Say the x-coordinate of this point is negative b over 2a plus t if t is positive. And the x-coordinate of that point will be negative b over 2a minus t. And it's easy to check. We can actually do that. It's easy to check that the value of f at these 2 points are equal. F at negative b over 2a plus or minus t is the same. Whether it's plus t or minus t, it's the same. We will use the fact that f can be written in this way. And so f at negative b over 2a plus minus t is a times, instead of x, I should write negative b over 2a plus minus t, that's x. Now plus b over 2a squared plus 4ac minus b squared over 4a squared. Naturally, you can see that b over 2a and negative b over 2a cancel out. And we are left with a brackets plus minus t squared plus 4ac minus b squared over 4a squared. And this here, we see that indeed the value of f at this point, whether it's plus t or minus t, stays the same. Because when you raise plus minus t to the second power, you simply get t squared. So indeed, the vertical line x equals negative b over 2a is an axis of symmetry. The parabola is symmetric with respect to the vertical line x equals negative b over 2a. Now the branches of the parabola point upward when a is greater than 0 and point downward when a is less than 0. Another interesting question for us to consider is when and if will the parabola intersect the x-axis and where the x-intercepts will be. Well, to do this, we can argue the following way. We can simply equate to 0 our function f, and because f is a brackets x plus b over 2a squared plus 4ac minus b squared over 4a squared. When we equate this to 0, we immediately see that because by our convention, by our agreement, a is not 0, we can divide by 0, and this will be equivalent to the expression in the brackets being 0. So we get x plus b over 2a plus 4ac minus b squared over 4a squared, this is of course squared, equals 0. And this in turn is equivalent to x plus b over 2a squared being equal to b squared minus 4ac over 4a squared. Now let's look carefully at this equation. We're solving it for x. The expression in the left-hand side of this equation is always non-negative because it's a squared. The expression in the right-hand side of this equation is a fraction. The denominator of this fraction is always positive. So the entire fraction will be non-negative if and only if the numerator is non-negative. And we immediately see that if b squared minus 4ac is negative, so the entire fraction is negative, this equation will not have any solutions. A non-negative number cannot be equal to a negative number. That is the first observation. If b squared minus 4ac is less than 0, then the graph of f will not intersect the x-axis. If, however, b squared minus 4ac is non-negative, we may proceed with solving our equation, and it will be equivalent to an equation where we take square root of both sides. Correct? So it will be root x plus b over 2a squared equals root b squared minus 4ac divided by 4a squared. Remember, during the first week we said multiple times that square root of x squared is not x in general. Square root of x squared is absolute value of x. So we then have on the left absolute value of x plus b over 2a. Now what do we have on the right? I can write this because b squared minus 4ac now by assumption is non-negative. This is always strictly positive. I can split the square root, correct? Root of a over b is root a over root b, provided of course that all the square roots here exist, meaning b is strictly positive, a is non-negative. So I will have b squared minus 4ac over root 4a squared. Now, let me leave root b squared minus 4ac the way it is and work a little bit with root 4a squared. Of course, 4a squared is simply 2a raised to the second power, and taking square root of that, I again get absolute value of 2a. Because 2 is positive, that is simply 2 times absolute value of a. All right. Remember when we talked about solving equations involving absolute values, the equation absolute value of x equals a, where a is greater or equal than 0, is equivalent to x being plus minus a. So this time we end up with x plus b over 2a equals plus minus root b squared minus 4ac over 2 absolute value a. Now note that absolute value of a is itself plus minus a. It's a if a is positive and negative a if a is negative. So because of the plus minus in front of this fraction, it's safe to omit the absolute value symbol altogether. Right? Because absolute value of a is either positive a or negative a, so you end up with plus or minus this expression without the absolute value. So I can write that x plus b over 2a equals plus minus the fraction b squared minus 4ac over 2a. And finally, we end up with the well-known formula. X equals, when you move b over 2a to the other side, we have that x equals negative b plus minus root b squared minus 4ac over 2a, provided, of course, that b squared minus 4ac is non-negative. So regardless of the sign of a, whether a is positive or negative, the quadratic function will intersect with the x-axis if and only if the expression under the square root called discriminant is greater than or equal to 0. Also note that if this expression is exactly 0, so this part disappears, and our parabola will intersect with the x-axis at only one point, negative b over 2a, and as we know, that point is the vertex of the parabola. So in that case, the parabola will touch the x-axis. Okay. Also note that if we look at this expression, and again recall that negative b over 2a is the axis of symmetry, we immediately see that the roots of the parabola, the x-intercepts of the parabola, are symmetric about the axis of symmetry. In other words, this distance equals this distance. The roots are symmetric about the axis of symmetry. Finally, the y-intercept is simply the value of f at 0, and of course, f at 0 is a times 0 squared plus b times 0 plus c, that is simply c. These are basic facts about parabolas and quadratic functions. If we forget something here, or if we didn't mention something that we need to mention, we will go back and mention it again. All right, let's look at an example. Draw the graph of the function x squared plus 4x plus 3. It's a quadratic function. And its graph is a parabola. Parabola is uniquely determined by any 3 points not lying on the same line. Any 3 points that are not collinear. It's an interesting fact. A parabola is uniquely determined by any 3 of its points, provided they're not collinear. That is, they don't belong to a line. Usually, when we need to draw the graph of a parabola, we want to find the vertex of the parabola and also check if the quadratic equation has roots. If it does, these 3 points usually suffices. Vertex and roots usually are enough to draw the parabola. So let us start with finding the vertex of that parabola. Remember, vertex has x-coordinate negative b over 2a, which in our case is negative 4 over 2 times 1, that's negative 2. And the y-coordinate of the vertex is easy to find by plugging negative 2 into the expression of the parabola. So that's negative 2 squared plus 4 times negative 2 plus 3. That is 4 minus 8 plus 3, which is negative 1. So the vertex is at the point negative 2, negative 1. Let us see if the equation has roots. Roots will determine the x-intercepts. You can use the formula that we just derived. That's one way. So using that formula, we have negative b is negative 4 plus minus b squared. 4 squared minus 4 times 8 times c. Divided by 2a. That will be negative 4 plus minus. That is 16 minus 12, which is 4. And root 4 is 2. So the roots are therefore either negative 3 or negative 1. I would also like to remind you of Vieta's formulas, another way to solve quadratic equations that occasionally is useful. Vieta's formulas. If x1 and x2 are roots, right, the sum of the roots must be negative the coefficient in front of x. So the sum of the roots will be negative 4. And the product of the roots is the free term. And very often you can simply guess what two numbers multiply to 3 and what two numbers add up to negative 4. And it's clear that these numbers are negative 3 and negative 1. So we can now draw this parabola. So the vertex is at negative 2. Roots are at negative 1 and negative 3. The y value at the vertex is negative 1. So the parabola will look like this. By the way, the y-intercept is at 3. So this point is 0, 3. And that is the graph of our function. X squared plus 4x plus 3. All right, this example is finished. Now, When we write our parabola in this form, when we complete the square, if we call this free term 4ac minus b squared over 4a squared as k, and this as b over 2a is negative h, so that x plus b over 2a is x minus h. Correct? We will be able to write our function after distributing a. I apologize, that is not k. We first distribute a over each term and then call this times a k. If you call b over 2a as negative h, or rather just as h, excuse me, as negative h. It's true. Then you can write the entire function as a times a x minus h plus k. So h here is negative b over 2a. What good is that? Well, when your quadratic function is written in this form, immediately you can see that h comma k is the point where you have your vertex. Sometimes that's useful. Okay, let us now look at this neat example. By the way, you can always find h and k either directly or by, again, by completing the square. I can take, just for the sake of practicing, I can take x squared plus 4x plus 3, the parabola of the previous example, and find h and k for this parabola. Well, we begin with factoring out the coefficient in front of x squared, which is already 1, so nothing to factor. Now we write 4x as 2 times x, and so it becomes clear that we will be squaring x plus 2. And of course, x plus 2 is x squared plus 2x plus, excuse me, x squared plus 4x plus 4. And x squared we already have. 4x we already have. To compensate for this extra plus 4, we need to subtract 4. And that gives us x plus 2 squared minus 1. So immediately we see that the vertex is at negative 2, comma negative 1, which we already knew. All right, that is the vertex form of a quadratic function. Now the example that I promised. we have a coordinate grid superimposed over the photograph in which a basketball player is throwing the ball, aiming at the basket. We need to find an equation for the path of the ball and try to understand if the ball will fall into the basket. So the idea is this. Let us look for our quadratic function. We look for f in the form ax squared plus bx plus c, because it's given to us that the path of the ball is the graph of a quadratic function. So here, of course, a is not 0. And it looks like the parabola passes through the origin. That simplifies life a little bit because we have f at 0 being 0, and f at 0 is a times 0 squared plus b times 0 plus c. That is, of course, c, and that is 0. So c is 0. That rids us of the necessity to find c. C is 0, and so f is simply a x squared plus b times x. We now need to find a and b. The easiest way to find a and b is to note that the vertex of the parabola, at least this point appears to be the vertex, has coordinates that are easy to understand. If this is -1, this is -2, this is -3, this is -4, this is 1, this is 2, this is 3, 4, 5, 6, and 7, and it looks like that point, which I believe is vertex, has coordinates -4, 7. So it appears that the vertex of the parabola is at the point -4, 7. So we can immediately write that -b over 2a, which we know is the x-coordinate of the vertex, is -4, which means that b over 2a is 4. And also we know that if I compute the value of f at -b over 2a, I should get the y-coordinate of the vertex, which is 7. Yet at the same time, the value of f at the point -b over 2a equals a times -b over 2a squared plus b times -b over 2a. Right? I'm using this expression, ax squared plus b times x. And when we do the algebra, we will get a times b squared over 4a squared minus b squared over 2a. So that is b squared over 4a minus b squared over 2a. That is, of course, negative b squared over 4a. And that needs to be 7. So now we have two simple conditions which we will consider as a system. On the one hand, negative b squared over 4a is 7. On the other hand, because b over 2a is 4, I can square this up. B squared over 4a squared will be 16. And now view these conditions as a system. It follows from this that if I divide one equation by the other, negative b squared over 4a over b squared over 4a squared, it'll be 7 over 16. Now if you do the algebra, it'll be negative b squared over 4a times b squared 4a squared which is exactly negative a, and that is 7 over 16. So a is negative 7 over 16. Now to find b from this, we can again use the circled equation. B over 2a is 4, because then b equals 2a times 4, which is simply 8a. And from this, we should be able to quickly find b, because this is just 8 times negative 7 over 16, which is, after cancellation by 8, negative 7 over 2. So that gives me b. b is negative 7 over 2. So now I am ready to write down the answer for the first question, the equation for the path of the ball, that is negative 7 over 16x squared minus 7 halves x. Or if you factor out negative 7 over 16x, what's left in parentheses is x plus 8. This, by the way, gives me the other root of the parabola. I knew one root was 0. The other root will be negative 8. And that point is where? Negative 5, negative 6, negative 7, negative 8. Now, how do we answer the second question? Does the shooter make the basket? Well, in order for the shooter to make the basket, the ball must pass through the point, I would say negative 7.5 and roughly 4. So what is the value at negative 7.5? the value of negative 7.5 is quite a bit below 4. It's actually exactly 1.640625, and it looks like the ball will not fall into the basket, it'll fall short of the basket. So it looks like the ball will fall short of the basket. It will not fall into the basket. Although, of course, it all depends on how we interpret the shooter making the basket. What does that exactly mean? The problem doesn't tell us. All right. Now, example 25. Find the vertex of the quadratic function. Rewrite the quadratic in standard form, which is vertex form. Well, it's another exercise in completing the square. So we start with 2x squared minus 6x plus 7. After factoring out a, we get in parentheses x squared minus 3x plus 7 halves. Now we write the second term as 2 times 3 halves times x. And now it's clear we will be squaring x minus 3 halves. And if you were to square this, it would have been x squared minus twice times 3 halves times x. That is good, we already have that. But then we will have an extra term, 3 halves squared. So to compensate for that, we need to subtract 3 halves squared from our expression. So we have x minus 3 halves squared plus 7 halves minus 9 quarters, which will be x minus 7 halves squared. So that is 14 quarters minus 9 quarters. That is 5 quarters. Right? And when you distribute 2 back, it will be 2 times x minus square of x minus 7 halves plus 5 halves. So we see immediately that the vertex is at the point I made a mistake, a slip of the pen. Somehow 3 became 7. So the vertex is at the point negative or positive 3 halves. Positive 3 halves, 5 halves. That is the vertex form of our parabola. Okay, the next theorem pretty much summarizes what we already know. If we have a parabola opening upward, a is greater than 0, then of course the image of our function, or the range, is simply f, the interval from f at the x-coordinate of the vertex minus b over 2a up to infinity. And if the parabola is opening downward, which happens if and only if a is less than 0, the image of our function is from negative infinity up to the y value of the vertex. This is really easy to write when your parabola is written in the vertex form, right? If a is positive, this parabola is opening upward, and f will take all values greater than or equal to k. And if the parabola is opening downward, f will take all values less than or equal to k. All right, a couple of examples here. Find the domain and range of a and b. Well, the domain in both cases is the entire real line. There's nothing to discuss here. Domain f equals domain g equals the entire real line. Now, what about the ranges? We see in example A, the parabola has the coefficient in front of x squared negative, so it's a parabola opening downward. So the image will be from negative infinity up to the y value at the vertex. Now the vertex is where? The vertex is negative b over 2a, so that's negative 9 over 2 times negative 5 2a, that is 9 over 10. And y is f at this point x, so we have negative 5 times 9 over 10 squared plus 9 times 9 over 10 minus 1. A little bit of algebra. Negative 5 times 81 over 100 plus 81 over 10 minus 1. Is that correct? 81 over 100 plus 81 over 10. So canceling by 5, that gives us 20. We have negative 81 over 20 plus 81 over 10 minus 1. Common denominator is 20. Negative 81 plus twice times 81 minus 20. That is 81 minus 20 over 20, which is 61 over 20. So the image of f simply is the interval from negative infinity up to 61 over 20, including 61 over 20. We are in this case. Now for function g in example B, that is a parabola opening upward, and so the image is simply the interval from this number k up to infinity. So the image is the interval from 8/11, including that point, up to infinity. All right, and maybe a couple more examples. In example 27, a farmer wants to enclose a rectangular space within her fenced backyard. She has purchased 80 feet of wire fencing, and she will use a section of the fence as the fourth side. So there will be no fencing here because for that we already used the fenced garden. We will only use fencing that we purchased for the other three sides. What dimensions should she make her garden to maximize the enclosed area? What is the maximum enclosed area? So the idea is this: we can build a rectangle like this, or a rectangle like this, or maybe a rectangle like this. All of them should have the property that the sum of the lengths of these three sides, 1, 2, 3, is 80. Naturally, we want to use the entire fencing we purchased to maximize the area. It's not immediately clear which one of these rectangles will deliver the largest enclosed area. That is what we need to compute, right? So either way, the total amount of fencing we're going to use, if we call this side L and this side W, so the total amount of fencing is L plus W plus L. Which is 2L plus W, and again that is going to be 80. Strictly speaking, it should be less or equal than 80, less than or equal to 80. But there is no need to leave unused fencing. Of course, the more fencing we use, the more enclosed area will be. So let us assume that we are using all of the fencing. So in particular, from here, width W is 80 minus 2L. Now the enclosed area, being L times W, simply is L times, instead of W, I write 80 minus 2L. And we see immediately that this is a parabola as a function of capital L. Area is a parabola opening downward. Roots are 0, and whatever L makes 80 minus 2L zero, clearly that's 40, so roots are 0 and 40. which immediately implies that the vertex is at the midpoint, which is 20. So the area is maximized when the length, one dimension of the garden is 20, and the other dimension W is 80 minus twice 20, so 80 minus 40 is 40. Now, what is the maximum area? The maximum area is well, 20 times 40, that's 800 square feet. All right, and the last example today is example 28. So we have here a rock that is thrown upward from the top of a cliff overlooking the ocean at a given speed. So let me draw a picture. So that is the cliff. That is me throwing the stone, a rock. That is the trajectory of the rock. It's known that the rock's height above the ocean can be modeled by this equation. Negative 16t squared plus 96t plus 112. Note that this seems to make sense because the parabola is opening downward. And there are three questions for us to answer. Question A, when does the rock reach the maximum height? Well, it will reach the maximum height at the point which is the vertex of this parabola. So to find the vertex, we compute negative b over 2a, which in this case is negative 96 over twice 16, which is negative 96 over 32, which is negative positive 3. I apologize, positive 3. So to find the maximum height, we compute simply h of 3. So when you do this computation, it will be negative 16 times 9 plus 96 times 3. 270 plus 18, it's 288 plus 112. That is 400 minus 90 plus 54, 144, and that is 256. By the way, what are the units? The x-coordinate here is time, so that is 3 seconds, and 256 is in feet. So that answers questions A and B. When does the rock reach the maximum height? In 3 seconds after being thrown. And what is the maximum height of the rock? The maximum height is 256 feet. Now question C, when does the rock hit the ocean? The rock will hit the ocean when h of t is 0. So we equate to 0 our equation, negative 16t squared plus 96t plus 112 equals 0. And when you solve this quadratic equation, the roots that you will get two roots. One of them is negative 96 plus 128 over negative 32. That is a negative number. Time could not be negative. We should ignore this root. And the other root is negative 96 minus 128 over negative 32. That is 7. So the rock will hit the ocean 7 seconds after being thrown. All right, this example finishes this fourth part of week 2, and week 2 is now over. Thank you.